Okay, so today we're going to talk about a new concept called energy. And I kind of asked this question that's on the screen, how much energy is in that heat? Because, well, energy is one of those subjects that there's kind of a lot of words you might use to describe. So sometimes you might like to say heat, and sometimes you might like to say energy, and there's probably a lot of different words you could use to describe heat. You might say something is hot or cold or warm or freezing or burning, or maybe you want to use the term energy, or maybe you want to be technical and say kinetic energy or thermal energy. There's a lot of different ways that we can talk about the concept of heat or energy. So the first thing to do is kind of describe these terms. What is heat? What is energy? So the technical definition of heat is the movement of energy from one object to another object that causes a change in temperature. So just think of this kind of in a hypothetical manner right now. Imagine you were to pick up, let's say you have car keys, okay? And you had left your car keys outside all night in the snow, and the moment you pick your car keys up, your car keys feel incredibly cold to your hands. Well, after a while of holding these car keys in your hands, another person picks up the car keys and says, oh, these car keys are rather warm. Well, what we have here is an example where heat has been transferred from your hand into the car keys. This transfer of energy causes a temperature change. So I know I used heat and energy in the same definition. Maybe we better back up and actually talk about what energy is. In science, one way of visualizing energy is as kinetic energy resulting from molecular motion. Atoms, molecules all around us are in a constant state of motion, unless, of course, the temperature happens to be absolute zero. We'll save that for another day. So suffice to say that everything you come into contact with, whether it's the gas that surrounds you, the water that's in the cup you're about to drink, or even the cup itself, the atoms and molecules are in a continual state of motion. This molecular motion can be thought of as a type of kinetic energy. Now, I know most of you are familiar with kinetic energy from physics, and you know that kinetic energy is defined as Ke equals 1/2 mv squared. 1/2 multiplied by m is the mass and v is the velocity squared. So we can think of a gas molecule moving through the air as having kinetic energy. And because air is a collection of a whole bunch of gas molecules, we like to think of the average kinetic energy of the entire air mass, let's say in the room you happen to be in. Well, there's a convenient idea here, is that, like, what if we were to find the kinetic energy of every single gas molecule in the room that you happen to be in, add them all up and divide, get an average. What are we going to say is that number? Here's where temperature comes in. Temperature, what we experience as temperature, is really defined as the measure of how much average kinetic energy we get from molecular motion. Temperature is a measure, indirectly, of the average speed of a gas molecule. Okay, so how are we doing on our definitions? What's heat? Heat is the movement of energy that causes a temperature change. What's energy? Energy is kinetic energy. It's combined motion of molecules, whether they are in a solid, liquid, or gas phase. How we measure kinetic energy is via temperature. If you were to hold a thermometer in the middle of a room, that thermometer is telling you the average kinetic energy of all of the molecules that are in that room. It works best when we're describing gases, but it's indirectly true for liquids and solids as well. So, okay, it's a lot to think of. Temperature is telling you how much average kinetic energy the molecules have. essentially how fast they're moving. Heat is the movement of this kinetic energy from one place to another place that causes a temperature change. Your hands coming in contact with an object of a much lower temperature can transfer heat from your hands into that other object. In other words, the fast-moving molecules in your hand come into contact with slower-moving molecules in a colder object, causing them to increase their temperature. Okay, so we're going to talk more about these definitions as we go on, but I just wanted to give everyone kind of a baseline. The important thing is we can quantify how much heat comes out of an object. We can quantify how much heat goes into an object by a relatively simple mathematical expression. Here we go. So the expression we're going to work with looks like this. Obviously, this is an equation, and it's going to have variables in it. And the variable we use to describe heat or energy is Q. So Q is defined as the amount of heat or energy. And honestly, at this point, if you still kind of, and you know, how do I say this? If you want to use the word heat instead of energy or energy instead of heat, you're okay. So for right now, the variable Q stands for how much energy something has, and that's my cute little expression for energy. Energy is measured in a very convenient unit. Energy is measured in something called calories, and it's almost the same as the energy unit you might have, let's say, on a Big Mac, but there is a slight difference between chemistry calories and food calories. Another unit of measure for energy is joules. Now, joules is a more, I guess I'd say, a slightly more scientific measurement of energy, but to make things easy right now, we're just going to stick with calories. So I want to calculate, this equation will allow me to calculate how much heat or energy goes into an object, or how much heat or energy comes out of an object. Now, to keep things a little bit clearer, we need to narrow down what this heat or energy actually is, what it's coming from. So before we go on with the rest of our calculation, we're going to skip back a page. So if I asked you some ways that I could, let's say, I know this sentence got chopped off, but what are some ways that I could increase the temperature of my car keys? You might say I could put my car keys out in the sun, or I could hold the car keys in my hands, or I could put the car keys by a fire, or even put them in hot water. And these are all perfectly valid ways to add energy to my car keys. However, some of them we're going to have to eliminate for right now. For now, we're not going to talk about how energy from the sun via light or photons can cause a temperature change. We're going to eliminate that one from our conversation right now. We are also going to eliminate the putting the car keys by a fire, because believe it or not, car keys being heated from a fire is a very similar method as to the car keys being heated by the sun. So if you notice the things that we have left, hold the car keys in your hands, put the car keys in hot water, these two things basically have the same thing in common, and they have to do with contact. So from now on in our discussion, we're only going to be talking about heat or energy transfer that's a result from direct contact. Okay? We'll come back to talking about the sun and fire in a bit. But for now, in this equation, just understand that this equation only really works if you put direct contact with the object. Okay, so we're back to our calculation. So this calculation will tell me the amount of heat or energy that goes into an object by contact or comes out of an object by contact. So this equation has to equal something, so Q equals. What are some important variables? Well, the first important variable is how much of that stuff do you have? if you pick up a large block of metal that's been sitting outside all night and you hold it with your hands, you won't really change the temperature of that object very much because it has a lot of mass. So the first variable to think about in this equation is just m for mass. So m stands for the mass of the substance in grams. What else is important, right? If you imagine putting a pot of water on the stove, is there a relationship between the temperature of the water on the stove and how much energy goes into it, right? So if I put a little bit of energy into the water, does its temperature immediately go up a lot? Or do I have to put more energy into the water to make its temperature go up a lot more? So this next variable we're talking about here has to do with temperature. If I put a little bit of heat into an object, the temperature is only going to go up a little bit. If I put a lot of heat into an object, the temperature is going to go up a lot. So this next variable has to do with temperature. So T stands for temperature, but it's not the temperature that you think. What we're really interested in here is what the change in temperature is of the object. So we assume the object starts at an initial temperature, and then I go and add heat to it. Let's say my object starts at 25 degrees Celsius, and I add heat to it, and the temperature goes up to 100. Well, did the object change its temperature by 100 degrees? No. The object actually only changed its temperature by 75 degrees. So this variable is a little confusing to people. This variable is what's called the change in temperature, or because whenever we're interested in the change in something, if you remember from physics, delta means the change in. You saw delta when it came to change in distance with respect to time. You learned that velocity is the change of distance with respect to time. You learned that acceleration is the change of velocity with respect to time. Delta x over delta t, delta v over delta t. So delta is the change in. So this variable that we're referring to right now is really the change in temperature. Okay? So before you start thinking that there's actually two variables here, it's not. Delta t just really represents one variable. Now, we'll talk about how to calculate delta t in just a moment, but we actually have another variable. As you may know, different materials change their temperature at different rates. Here's a good experiment you can conduct on your own. Take a pot of water, put it on the stove, turn the heat on. After 1 minute, maybe you don't want to conduct this experiment at home. After 1 minute, most of you know that touching the pot will burn your hand. But touching the water will still be cold. The pot and the water both absorbed the same amount of energy, yet the temperature of the water has barely gone up at all. The temperature of the pot is hot enough to burn you. So we need another variable to describe the ability of an object to absorb heat or the ability of an object to release heat. In this variable, I'm going to use the variable C because C stands for something called heat capacity. I know it's a strange term, but let me just kind of put this down here. Oops, we lost it there for a second. So heat capacity is basically, I'm trying to think of a way to describe heat capacity pretty simply. Heat capacity is the ability of a material to change its temperature when energy is added to it or released from it. Let me give you an example of heat capacity. Heat capacity of water. So usually I'm going to write this. I'm going to put heat capacity and then I'm going to put H2O. That's literally defined as the heat capacity of H2O. It is defined as 1 calorie, I'm going to abbreviate calorie with CAL, per 1 gram per 1 degree Celsius. Here's what this means. If I had 1 gram of water, okay, and I wanted to make its temperature go up by 1 degree Celsius. So I want a delta T of positive 1 degree Celsius. Now that could mean going from 0 to 1. It could mean going from 2 to 3. It could mean going from 99 to 100, as long as it's a 1 degree change. What this says is I would have to add 1 calorie of energy in order to make that happen. Now, if I compare this to something like, let's say, aluminum. Hold on, I lost my screen for a second. If I were to compare this to something like aluminum has a heat capacity of, first of all, it's very different from water. Aluminum has a heat capacity of 0.215 calories per 1 gram per 1 degree Celsius. Now, if I had a similar, what this means is if I had a similar 1 gram piece of aluminum and I wanted its temperature to go up by 1 degree Celsius, so let's say delta T of positive 1 degrees, now I would have to add 0.215 calories of energy in order to make that happen. So if just kind of compare the two right now, they have exactly the same mass of aluminum and the same mass of water sitting side by side. The water requires about 5 times more energy to make the same temperature change as the 1 gram of aluminum. Another way to say that would be the 1 gram of aluminum requires 5 times less energy to make the same temperature change as water does, that same 1 degree change. Now, heat capacities like this for water and for aluminum are tabulated. Heat capacities are intensive properties. They're very similar to density in that the density of an object doesn't change regardless of how much of it you have. The same thing with heat capacity. Heat capacity of an object does not change no matter how much you have. And I don't expect you to memorize these. Heat capacities will be given to you. So the heat capacity, you just kind of have to get used to it. It's another variable you require when you want to calculate how much energy goes in or out of something. So heat capacity is going to be multiplied by mass, and then mass is going to be multiplied by this temperature change. Let's talk about temperature change and how to calculate it, and then we're going to solve a couple problems. So temperature change is actually just that. It's what the temperature change is. Anytime you see the delta notation in front of anything, delta anything is always the final value minus the initial value. So now we just want to apply that to delta temperature, change in temperature. That means it's going to be the final temperature of the object minus the initial temperature of the object. So the example we gave earlier, if I had an object that started at 25 degrees Celsius and energy was added to it and its final temperature made it to 100 degrees Celsius, the change here is not 100 degrees Celsius. The change is the difference between 25 and 100. So my initial temperature is where I start, that's Ti. My final temperature is where I end up, Tf. I just have to worry about figuring out what the difference is between these. So to find delta T, I need to just basically subtract these two, but in the right order. So the final temperature, in this case delta T, equals the final temperature 100 minus the initial temperature 25, and this is where we get the 75 degree change in temperature. You could say positive 75 degree change. It is possible sometimes for the temperature to drop and have a negative temperature change. It takes a while to get used to the idea of temperature change. So let's go back and put all of this together and we'll solve a problem, okay? So here's a sample problem. How much heat is required to raise the temperature of 100 grams of water by 50 degrees Celsius? Well, what variables is the problem giving you? The 100 grams is the mass. It says water, so we would know to look up the heat capacity of water. The heat capacity of water is 1 calorie per gram degree Celsius. And the only other thing we need to know is the temperature change. Does the problem give you the initial and final temperature? Well, no, it doesn't say where it starts and where it ends, but what does this mean? What is the by 50 degrees C? That's the change. So we have all three variables we need. Let's plug them into the equation and solve this. Q equals C times M times delta T. If you want to put delta T inside of parentheses to know to do that part first, that's fine. So Q equals C. For water, this is just 1 times the mass, 50 times the temperature change. I don't know where I got 50 from, sorry. The mass is 100 times the temperature change, 50. Well, that's just 100 times 50, and we are looking at a temperature change, an energy change of 5,000, right? So, well, what's the unit here? The unit is calories. So 5,000 calories would have to be added to this 100 grams of water to make its temperature go up by 50 degrees Celsius. So it doesn't say where it starts and where it ends. I could have a 50 degrees Celsius change if I went started from 10 degrees Celsius and went up to 60 degrees Celsius. That would be a 50 degree change. Or it would work if I started from 50 and went up to 100. That would also be a 50 degree change. They would require exactly the same amount of energy to do this. All right, let's try another problem. Okay. So in this problem, we've got a 100 gram piece of aluminum absorbs 1,000 calories of energy. You could assume that because it says absorbs, that means heat is going into the object. So if the initial temperature of the aluminum is 25 degrees Celsius, I'm just going to say the 1,000 calories is Q. What's the 25C? Is this the change in temperature? Well, let's read the rest of the question. It says, what's the final temperature? Okay, so what this problem is saying is this can't be the final temperature. It's also not the change in temperature. That has to be the initial temperature. The problem is looking for me to find what the final temperature is. All I need to solve this problem, it says it's aluminum, so I know that the heat capacity of aluminum is 0.215. So in this problem, you can solve it a couple ways. You can try to rearrange the equation, or you can just try to plug and chug the numbers. So let's just put the equation down here and put these numbers in it. So I've got Q equals C times M times delta T. So I know the heat is 1,000. The heat capacity is 0.215, and I'm just putting it in parentheses to make it easy for me to think about it. The mass is 100, and then delta T, we're going to have to split this up. So delta T is the final temperature, which I don't know what it is, minus the initial temperature, 25. So that's our problem. The problem has one unknown, but unfortunately the unknown is kind of buried inside this problem. So alternatively, you could try to rearrange this equation to solve it. But what I want to do is I just want to solve for TF directly. So I'm going to multiply 0.215 times 100. So I get 1,000 equals 21.5 times TF minus 25. Now I can't just divide away the 21.5 here. I really have to actually, I am forgetting myself. We can divide this. So if I want to get TF minus 25 all on its own, I am going to divide both sides by 21.5. Oops, there we go. So if I do this, it gets rid of the 21.5 on this side, and then I'm going to have, let me scroll down the page here. There we go. So that's going to cancel out 21.5 here. I got 1,000 divided by 21.5. 1,000 divided by 21.5 gets me 46.5 equals TF minus 25. So to do this, all I have to do now is add 25 to both sides. And if I do that, so this cancels out 25 here, and I end up with TF equals 71.5 degrees Celsius. So basically this says the temperature is going to go from a starting point of 25 to a finishing point of 71.5 degrees Celsius. So this problem is a little bit more work, but it's not any different than any other problem you're going to see. Okay, so that's all I wanted to show. I'm going to give you a bunch of sample problems now to work on, and there it is. All right, good luck.